Hello, Math 5a. We're going to give a little introduction to the reading for this week. So we have three sections. We have 5.2, which is on log functions. We have 5.3, which is on the natural base. And we have 5.4, which is on log scales. These sections are really important in real life applications. So we learned already about exponential functions. Right, exponential functions, and these functions are used for modeling things that grow very fast, right? So you have something that blows up like this, fast growth, or also fast decay, right? So you could have an exponential function that's decreasing fast decay. And it shows up all the time in the real world, these exponential models, this kind of growth, right? It's a very basic thing that happens a lot. So those are exponential functions. We're used to people saying like, oh, this thing grows exponentially, meaning very fast. And sometimes they mean technically exponential, sometimes they just mean fast, right? But there are other ways things that can grow, right? They don't have to grow really fast like that. You might have something that grows slowly, right? And that's what log functions do. So log functions are the inverse functions of exponential functions. So one thing that means is that they're a reflection across the line y equals x. So graphically, if you took the line y equals x, which is a straight line through the origin with slope 1 like this, and if you, when we say it's a reflection across the line y equals x, I mean if you put a lot of ink down on your exponential function and then folded it across that dashed red line y equals x, it would plop down your log function on the other side. So the log function is going to look like this. Instead of having this horizontal asymptote over here, you're going to get a vertical asymptote along the y-axis. Instead of going through 0, 1, we're going to go through 1, 0. And then it grows. It does go off to infinity. It's hard to tell from the way I've drawn the graph. It does go off to infinity as x goes to infinity, but it goes very slowly, right? So it's a very slow growth. And so this is a good model for something that does grow. It gets bigger, but it's slow growth. Slow growth. I can't write, apparently. Slow growth. Okay, so those are anything that has a very slow growth is the kind of thing we want to model with the log function. So also useful in the real world. The natural base. So, we can study exponential functions with base 2 or base 3 or base 1.5 or base 10, right? There are all these bases that we use all the time. And there's one that's called the natural base, both for exponential functions and the corresponding inverse log function. And so in the exponential world, that's y equals e to the x. So first of all, e is a number, just like e is a number, just like pi is a number, right? So pi is a number. It's about 3.14. E is about 2.718, something, right? Also has an infinite non-repeating decimal point, just like through pi and infinitely many other numbers. But E is really special. When I'm working with them numerically, I think of them both as being close to 3. Pi, it's a little bit bigger than 3. E, it's a little bit smaller than 3. They're both close to 3, right? So when I look at this y equals e to the x, I'm thinking, oh, it's pretty close to 3 to the x, right? It's going to behave in very much the same way. When you go to take calculus, which we hope you all do, you'll learn about these things called derivatives. And the derivative tells you how fast your function is changing at any point. And when you take the derivative of a function, normally you get a different function that describes the rate of change at any particular point. So the derivative of x squared is 2x. The derivative of sine of x is cosine of x. There are always, it's a different function, usually. But the exception is this fancy function y equals e to the x. It's really special because the derivative, which tells you how fast it's changing, is exactly the same function. And that doesn't quite work for other exponential functions. If you have y equals 2 to the x, y equals 3 to the x, it doesn't work. You have to modify those ones a little bit. They're not as special. Y equals e to the x, you don't have to modify at all. It's exactly the function for which that's true. And in fact, sometimes that's how people define the number E, is the number, the only one for which that property holds. So that's why we consider it the natural base, even though E might not seem very natural to you at first, right? 2 or 3 might seem a lot more natural, or 10, but this is why we consider it sort of the natural base. And it has a corresponding inverse function, just like 2 to the x has log base 2, and 3 to the x has log base 3, and 10 to the x has log base 10. We have the corresponding inverse function, log function is ln of x, which is ln is for natural log. It's not in, as sometimes it looks like it is when it's written. It's ln for natural log of x. I think it might be French, right? Like log natural, I'm not sure. So this is the natural log. And it's just so special that it gets its own notation, but it's the same as log base 2 or log base 3. It's just log base e. So this is the same as if you wrote log base e of x. And so when you're first learning about it, you might want to do that. Anytime you see natural log of x, you might want to rewrite it as log base e of x, so you can remind yourself that this is all it is. It's just another log function. It just has this base of e down here in this subscript. And so, but it works the same, all the same properties, everything else as all the other log functions. So you can do that as sort of a tool when you're learning this at first, but you should try to switch over to natural log of x, because it's sort of the more sophisticated way, right? That's what people will use if you're out trying to communicate with other scientists and stuff. So we'll try to switch over to that. And log scales. So M5a, we've designed this course almost exclusively to prepare you for calculus, even though, as we've said before, the skills you learn here are more central to all your other science courses than calculus itself is, right? The skills you really need in science courses in real life are the skills you're learning in pre-calc, much more so than calculus. Log scales is like that too. Log scales is one of the very few, maybe the only topic that we're studying in pre-calculus that's not like 100% we need this for calculus, right? But it's also one of the topics that is most used in the real world. And so the book gives a really nice introductory example to log scales, where they say, okay, the way you use, why you would want to use the log scale is if you want to compare things of wildly different sizes. And they have this really nice example where they're talking about like the mass of different animals, right? And you have these huge animals that literally weigh a ton, right? And then you have these tiny little things that barely weigh anything at all. And they're all animals, right? We want to talk about them in the same scale, but the sizes are so different that to even talk about them, you would normally use different units, right? But if you put them on a log scale, what you're doing essentially, because logs are exponents, is you're saying, what's like the number of zeros, essentially, is what you're asking yourself. Like, how big is this in terms of decimal point places, right? So that's why the log scales just say, how many decimal point places are you talking about? Another example that you might want to use to compare where log scales might be appropriate is like, how much money do I have versus how much money does Jeff Bezos have, right? You need to count the number of decimal points, right? To even talk about it, right? They're not even on the same scale. And so the log scales help us to compare things of wildly different sizes. There are also log scales that we use all the time in daily life without even thinking about it. Decibels for like how loud is a noise, because some noises are really, really loud and some you can't hear at all, right? And so we have these, again, it's sort of an exponential difference. The Richter scale, measuring the size of an earthquake, right? The magnitude of an earthquake, how big is the earthquake? It increases so fast that we use a log scale to compare those things. There's another one that we use all the time, Richter scale. The pH scale for acidity of substances, right? Is it really acidic? Is it really basic, right? Those things differ, right, exponentially. And so we take the log, which just asks what is the exponent, right? And so you can talk about those linearly in order to compare exponential differences is essentially what's going on there. So I really hope you appreciate this section, these two sections, because it's really, really, really the kind of stuff that's showing up in real life and in sciences all the time. So I hope you find it helpful and enjoy it.